So our work with MapReduce on Azure started with MapReduce roles for Azure. So we built the decentralized MapReduce framework for Azure, utilizing these high available and scalable Azure infrastructure services as building blocks. So we selected the Azure platform because when we started building this, there weren't any distributed computing frameworks available for Azure. So we did the first release of MapReduce roles for Azure back in fourth quarter of 2010. So if you're using MapReduce roles for Azure, this supports just traditional MapReduce paradigm, and then this hides the complexity of the cloud, and you just need to, so in Azure terms, they say you just need to worry only about your application. So in Twister for Azure, in MapReduce roles for Azure, we just let you worry only about the map and reduce task, and don't even worry about the cloud services, and we take care of everything in the underlying MapReduce layer. Yep. So this is the architecture of Twister for Azure. So in there we use Azure queues for task scheduling and Azure blob storage to store input and output data, and then Azure tables to store the monitoring data as well as for some coordination. Yeah. So Twister for the MapReduce roles for Azure also provides the combiner step of Hadoop MapReduce, and as well as the local development environment and the web-based monitoring console as well. So this has been the foundation of Twister for Azure, which is the iterative MapReduce framework, which we'll have a detailed look later. So let's have a look at the data-intensive iterative applications. So these kind of iterative applications are at the core of vast majority of data-intensive scientific applications we can see today. So these these includes most of the clustering applications, a lot of data mining applications, machine learning, dimension reduction. So most of these applications fall into this category of data-intensive iterative applications. So this class of application has been growing in the recent times, mainly because of the need to process very large amount of data, as well as the emergence of these new data-intensive computational fields, such as bioinformatics, chemical informatics, etc., and web mining. So these applications most of the time has the structure where you have a loop and then you do some processing, and then you have a combined step where you do a post-processing of the data you process in the iteration, and then you deliver to the next iteration, and then you go onwards. So the nice thing about these type of applications is this map perfectly. So if you look at the iteration of these applications, these match perfectly with the MapReduce paradigm. So most of these applications consist of these iterative communication and computation steps, where we can see this single iteration as a MapReduce computation. So you can see we have large input data, and then we have a reduce step, and so this part would be a MapReduce computation. So another characteristic of this data is the usage of very large loop invariant data. So there would be some data that you would only need for the processing within the loop, and those data won't change in between iterations. And then you would have the results of the iteration, which is the loop variant data, which needs to be transferred to the next iteration. So if you look at the earlier figure, so whatever the data you process here would be the loop invariant data. So this data don't change, and the size of this data is very large. Yeah, and then this whatever the result of the iteration needs to be broadcasted to all the compute nodes in the next iteration. So we see this fitting perfectly with the single iteration of such applications fitting perfectly with MapReduce frameworks, but you can also, you can think that we can also process, why can't we do this with traditional MapReduce frameworks? You can create your own driver program which will take care of looping between the MapReduce frameworks. But the thing is, like, the traditional MapReduce frameworks are not efficient for this type of computations, because they don't take care of the obvious characteristics of these applications, like the ability to cache data and this loop invariant data. And then they also don't provide efficient scheduling of tasks between the iterations. So because of that, we came with this iterative MapReduce frameworks. So yesterday, Judy introduced you to the Twister iterative MapReduce framework, which is good for HPC clusters, local clusters, as well as clouds. So now we introduce you the Twister for Azure, which we developed for the Azure cloud, specifically designed to coexist with the cloud characteristics. So first, we'll have a look at the extended program model of Twister for Azure. So in Twister for Azure, we extended the MapReduce program model with a merge step, followed by a broadcast or a scatter step. So, and then Twister for Azure also supports additional input for the map and reduce tasks and for the merge task. So this can be used to deliver that loop variant data, which should be broadcasted or scattered through the iterations. And then Twister for Azure considers the normal input data of MapReduce computations as the static loop invariant data. So those would be the traditional MapReduce key value pairs, and these are comparatively large size. And then so we have the ability to cache them between the iterations. Yeah, so let's have a more detailed look at the merge step, which we have here. So in Twister for Azure, the merge step receives all the outputs of the reduce computations, and then it has the ability to broadcast this data to the next iteration. So why we need this is to collect the outputs of the reduce task, and then perform any post-processing of the iteration, and then also to decide whether to go for next iteration or not. So since Twister for Azure is operating on a decentralized architecture, we don't have any centralized master or a centralized driver which has a which can take this centralized decision of whether to go for a new iteration. So the merge task is also responsible for taking that decision whether to go for a next iteration or not. And then the merge task receives the output of this iteration, as well as it also can access the output of the early iteration if it needs to do some computations. I mean, if it needs to, like, let's say, calculate the difference between the outputs of the two iterations to decide whether to go for a new iteration or not. So another thing is Twister for Azure supports multi-level caching of that loop invariant data. So this is like comparatively very large size data. And so Twister for Azure supports multi-levels of caching. So first is, so since this is a iterative MapReduce framework for cloud, our input and output data is typically stored in the Azure Blob Storage. So if so the Azure Blob Storage is off-instance storage, so you have to fetch it from somewhere else in your data center, and then it has high latencies, and then the bandwidth is not that high. So in such scenarios, it makes it much sense to cache the data. So Twister for Azure supports caching this input data in the disk, as well as in memory, as well as like directly in memory in the process itself, as well as using memory map files. So I'll talk a little bit about why we are using memory map files in a later slide. Yeah, so Twister for Azure supports, so another feature of Twister for Azure is this cache-aware hybrid scheduling. So, so since Twister for Azure do not have a centralized controller or a driver who has the global knowledge of where the data products are cached in our cluster, so we need to come up with a cache-aware scheduling mechanism. So in here we kind of turned it upside down and then made the workers pick their task which they would need to process. So it's so whenever iteration is over, Twister for Azure will advertise that, okay, we have a new iteration in a centralized job bulletin board, and then all the workers will be listening to this board, and then whenever they see a computation, I mean a new iteration in that job board, they'll check their local data cache, and see whether they have any data products, cached data products that would need for that computation. So if they have any data products, they'll pick up a task from that computation and would execute. So in this case, we also added metadata caching support also to the worker nodes. So they don't even need to fetch metadata for the map task. So this makes the scheduling of the things very fast and efficient. But the issue is whatever happens if some node goes down, or whatever happens if nobody picks up a task. So in such cases, these whatever the remaining tasks would be added back to the scheduling queue. So Actually, I forgot to mention. So the first iteration, the initial iteration of the computation would be scheduled using the traditional scheduling queue, like which would be Azure queue. So, and then whatever the leftover task of the iterations would also be added back to the queue and would be scheduled in a similar manner, which should ensure that we have good fault tolerance and the eventual completion of your computations.